Chapter 7 is applications of vectors, and our first section, 7.1, talks about vectors as forces. Before we get into that, we're just going to do a little intro of Chapter 7. So we've been talking about basic ideas of vectors, physical situations, and mathematical situations. So we have some properties of vectors down, and understanding things like magnitude and direction, some basic calculations, vectors from Chapter 6. We're going to get into discussion of more of application vectors in the physical world, more of a physics application, and more geometric vectors in this particular chapter. In 8 and 9, as we finish the course, it'll be more algebraic vectors. But you guys have some physics background in grade 11 physics. Some of you have been taking grade 12 physics. You're going to understand this more currently than I will be, and that reason why we're going to just go through this relatively quickly and get a few examples done and things. So we've done some calculations with velocity and plane flying and wind condition situations, force of two or more objects working together, boating applications, water and currents, and we're going to talk about a little bit more of those in some and the chapter with discussion of multiplication of vectors and the different ways that you can do multiplication of vectors. Okay, so our learning goals and success criteria are follow here, some application questions, operations of dot products and scalar vector projections that we're going to talk about, and we're going to learn how to do all of these and set some groundwork for the remainder of the course here. Okay, so right off the bat here, vector force, we just need to do some definitions here. Force is a vector that's measured in newtons, and 1 newton is equal to 9.8 kilograms per meter per second squared. Resultant forces are a combination of a system of forces. So our resultant force gets calculated by looking at all the forces that go into building a system. Here's our first example. I'm going to cut to the whiteboard here in a second, but here's our first example. We've got a force of 1,000 newtons going in a direction of north 30 degrees east, and a force of 2,000 newtons going in a situation in east direction. So in this case, our boat is going to be down in this area, and we've got a force pulling on this, okay, like a tow, and a tow cord pull attached to the boat, pulling in the 2,000 Newton force in the east direction. And the blue resultant vector represents where this boat and how this boat is going. So I'm going to pause and get back to doing this right now. Okay, so here's the situation with this particular example. It's already been drawn into a parallelogram. So basically, I've done some calculations here that I just have to go and find this resultant vector and then the direction. So it is a relatively quick calculation here. The first thing I'm going to do is use my cosine law. Okay. And that's going to be 2,000 plus 1,000. I'm going to, okay, so then I've got my two sides times the cos of the interior angle, 120 degrees. Now, I'm going to leave all the calculations, okay? Make sure that you do square this, so it's going to be the square root of this expression, right? Okay, and I get the calculation after crunching all these numbers. I get it to be 2,645.75 newtons. Okay, and I think that's a sensible answer. Okay, it looks by scale. It's not quite to scale, it might be, but it looks like that resultant vector is going to be a little bit larger than, just based on the angle orientation, a little bit larger than force 1 vector here. Okay, that should have been a force 2 here. Okay, the direction. Okay, I'm going to use the sine law. Okay, I want to find this direction here. Okay, so I'm going to set this up really quite easy. We've done some of these before, quite a few of these. Done. Hopefully you've done some of these questions back in grade 11 math. cross multiply and after a little bit of work here I get 19 degrees. So that's this 19 degrees here as a vector orientation, and I should answer, get my final answer similar to the way the information was given in the question. So I need a sort of a compass orientation with this one, and that will be this calculation here. Okay, so if I just real quickly subtract 19 degrees from 90, that gives me 71 degrees, and that bearing is north 71 degrees east. So my resultant vector, I should write the statement and include the direction here. That's it. Okay. Okay, when we have more than one force vector, okay, or a system of vectors, combination of vectors, we can add the components together. We can talk about the x components and the y components, use a little bit of basic trigonometry, okay, and do the string, okay, do the string of vectors here, okay, and then employ sort of the resultant x component and the resultant y component to find my total resultant vector, and then to find an orientation, use these same ratios here. So we're going to work through a large system of forces here, quite a number of things, and we're going to look at each one individually as we move along the x-axis. So this one, this one, this one, 4, 5, 6 combination of vectors, and we're going to use the individual forces here. Okay, let's see if we can work through this example. Okay, our first component here, this force of x, is going to be found, let's start with this triangle here. So it's 60 degrees off the x-axis. We always want to do it in relation to the x-axis. So our combination resultant vector of our x components is going to be 15, right, times the cos of 60 degrees. And that's just for this first one here. That's this vector right here, okay? So I'll go in a sort of a counterclockwise direction. Okay. The next one, okay, is going to be this vector right here, okay, and that will be 10 times the cos of 90 degrees. Okay, that's that. Okay, so now I'm on this vector, that'll be 5 cos 180 degrees. Then I've got 7.5 times the cos of, looks like I've got 180 plus 45, 225. Now, doing it this way with components is going to generate a couple of negative signs, and that's fine, okay? That's fine, no problem, because we've got forces going in an opposite direction. Okay? We want to remember we want a resultant x component force here, and if some are pulling, okay, some of these forces, individual forces, are pulling in a different direction or a different orientation, and then there's going to be a negative effect on it. So we're on this one, we're back to this one here, so that'll be 12.5 times the cosine, and it's all the way around, so it's, okay, so it's 3/4, that's 270 plus 60, 330. Okay, and then I've got my last one, okay, and that's plus 10 the cos of, now that can be either 0, okay, or 360 degrees here. Okay, to give us the same number, I'm just going to use 0. Okay, we're back to the x-axis here. So we've got a string of numbers here. Okay, cos of 15 times the cos of 60. I've got in my notes 7.5. Okay, the next one, cos of 90 times 10 is 0. Cos of 180 times 5, okay, is negative 5. Okay, and there's that opposite direction, right? 7.5 times the cos of 225. I've got, now I've rounded this one off, negative 5.3. Then I've got a 10.8 here. I think that was cos 330 multiplied by 12.5. And then I've got a 10. Is that all of them? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Good. And I've got a total of 18 newtons. Good, good. Now, I'm going to write the same string for my y component. Okay, I think you guys can probably do this. Maybe you've done this before. I'm going to start again at this vector and go all the way around. And see if I can write my string here. Okay, let me pause this. And okay, so the corresponding force vectors for all my y components, my individual string of the system here is, first one is sine of 60, okay, multiplied by 15. We've got 10 sine 90, and we've got 5 sine 180. We've got 7.5 sine 225. The same angles apply. And then 12.5 times the sine of 330, and then back to my starting point here, 10 times the sine of 0, or 10 times the sine of 360, if you like. They work out to be a string of 13, 10, 0, negative 5.3, negative 6.25, and 0. And I've got a total resultant y component vector of 11.45 newtons. Here, now we've got to do our rough little calculations here. Our total resultant vector will be 18 squared, 11.45 squared. I get a total resultant vector of 21.3 newtons. And my orientation, okay, it's just the ratio of the tan of theta, okay, over my opposite side, that's y, over my adjacent side, that's 18. I get theta to be, okay, after a little bit of inverse tan, 132 degrees. That's an orientation, okay, again, to the x-axis. That would be north, if I do my calculations correctly, 58 degrees east. So my resultant vector, let's bring it all together. Okay. It is 21.3 newtons north, 58 degrees east. So what this means is that if I had, okay, position here and I had forces pulling on each of these positions, the resultant vector would be 21.3 north, 58 degrees east. Okay, so it would be, okay, going off in like this. Okay, that looks almost like, because these three together, these four together, 1, 2, 3, 4, okay, are moving this and counteracting these ones here. Again, that's a rough sort of explanation of what's going on here, but okay, that's a way to look at it and understand it. Okay, let's get into the next example. Okay, the concept of equilibrium. Okay, a state of force is in equilibrium if it's in a still position. Okay, and it can make this triangle. They're coplanar. The forces are coplanar, and we can look at a combination of forces being in equilibrium if we can get a situation like this. Now there's a couple of principles here that help us get this. First of all, the coplanar idea, for sure, absolutely is important here. Okay, the forces are coplanar, then they're in equilibrium. Now the other concept here, and we use this in homework, I'm going to use it down here for this example, is that the largest magnitude, okay, is less than the sum of the other two magnitudes. That allows us to set up sort of a linearly dependent, or linear combination situation. So in this case, okay, find if a system of three forces, okay, where 12, 13, and 5, it can be in equilibrium. So if I've got the largest side, okay, and it's less than, okay, the sum of the other two sides, so 12 and 5 here. 12 and 5 is 17, that certainly is larger. So yes, it's in equilibrium. That's all we need to do here. Now, some of you might notice, okay, that this is a Pythagorean triple. Okay, so if I had, this would also hold. This doesn't always work, okay, certainly. Okay, but this is a balanced equation. It's called a Pythagorean triple. Okay, and what this means is that it's actually a right triangle. draw this as a right triangle here. So there we've got a coplanar situation. These three forces can actually make up a right triangle here. And that would again be a particular case of a question like this. And it's only because I recognize that as a Pythagorean triple. But that's what it would look like. Okay. Next one here. Nice little example from the textbook here. Caleb pulls a rope attached to her sleigh with a force of 200 newtons. There's a diagram that represents this. If the rope marks an angle of 20 degrees with the horizontal, determine the force that pulls the sleigh forward. Okay, the force that pulls the sleigh forward is this force right here. Okay, that makes up a triangle. Okay. And we could find that right triangle here. I would use, it's adjacent side, so I would use, I'm going to call this resultant, I'm going to call this force X. Okay, so I would have force X, which I want to try and find, over 200, is equal to what trig ratio here? That's adjacent over hypotenuse, so that's the cos of 20 degrees. And cross multiply. Okay, that would be, just going to go to my calculator here. Okay, about 187.9 newtons. Okay, that would make some sense here. For B, the force that tends to lift the sleigh forward. So if Kayla's pulling this sleigh on that angle, there's going to be a force that pushes forward, that pulls the sleigh forward, and a force that tends to lift the sleigh upwards. Okay, that'll be the other one. I'm going to call this one, okay, Fy, and that'll be the other. That's the opposite. Okay, the opposite side, so that's a sine ratio. Okay. Okay, much smaller. Okay, we know that sine of 20 degrees is a much smaller ratio, multiplied by 200. Okay, that's about 68.4 newtons. That's how we handle a question like that. That sort of gives you a perspective and a context here. Okay, this one's going to take a little bit of time here. I want to establish what we've got here. Find the tensions in each string brought on such that the body is set at equilibrium. Okay, so it looks like this here. We've got maybe a sine 100 Newton meter force by gravity that's being supported by these two tensions. And I want to find, I want to show both examples here. Okay, showing it in geometric vectors and showing it in scalar components here. So I'm going to use a smart whiteboard, set this up. We've got some diagrams here. I'll put the solutions up here really quickly. I won't walk through it, and we'll get back to you in 1 minute. Okay, I've just written the solution here. I think it's going to be okay. Notice what I've done with geometric vectors. I've moved the first vector, that's the second tension force. I've moved it up here to the end so that the tail of the tension vector, the second tension vector, is attached to the head. I've made a triangle basically. Okay, so I'm adding these vectors here. So the third tension vector, okay, counteracts, okay, is equal to, okay, 100, because it counteracts, okay, the sign going down by gravity here. That's this one that we've got here on this diagram. So I'm actually moving two vectors in a lot of ways. I'm moving the tension 2 force vector, and I'm moving the equilibrium vector up here to close off my triangle. I use some basic principles of triangles and parallel lines to get these angles, and I can set up a sine law, actually two sine laws here. First one to solve for T1. Okay, that'll be the length of T1 over the sine of 60 is equal to 100 over sine of 80 here, and I work that out, cross multiply, I get T1 to be 88 newtons. Similarly, I do T2 this side here, and that's across from 40, so that's this ratio right here, and that's equal to the same 100 over the sine of 80, cross multiply, and get my two answers here. Okay, leave that there if you guys want, and sort of see how you work on that, and we'll get on to, method 2 of solving it algebraically, and we should get okay, with scalar components, we should get the same answer for both, and that'll be the challenge. Okay, with scalar components, I have to take a look at my x resultant component here, and that's going to be, okay, so I'm going to go with respect to, okay, so T2 times the cos of 30, okay, and then I've got T1 times the cos of 130. That's this angle right here. Okay, I don't have to include T3. That's okay. There's nothing along the x-axis. It's all along the, okay, the T3 is all along the y-axis. So when I work this out, okay, I get, okay, Rx, okay, okay, the resultant x is not, there's nothing along the y-axis. It's all along the y-axis. So this I know is 0, and I get a negative 0.643 times T1. I'm just going to rearrange that. I'm going to use these as variables here. And then a plus 0.866 times T2 vector. And I'm going to treat these as variables here. Similarly, Ry, okay, just has a little bit of a different orientation here. Okay, so Ry, okay, Ry, okay, has a T1 of sine of 130 and a T2 times the sine of 30 degrees. Okay. And Ry actually, okay, is 100. Okay. So now I have the situation where I think I've got 0.766 times T1. And then the sine of 30, you've got 0.5 times T2 here. So my system is determined by, okay, these two things here. Now, if I try and, okay, solve for, rearrange it and solve, yeah, I can set up, I could solve this one here. I could rearrange this. Let's move that to 0.643 T1 equals 0.866 T2. Okay, let's solve for T1. Okay, so now I can substitute this into here. Okay, so wherever there's a T1, I could solve by substitution. I've got 0.5 T2, okay, and this equals 100. Okay, I could work this all out. I would get, okay, and again, all I'm doing is solving a system of equations. I get T2 to be 65.3 newtons. Okay, and then I back substitute, okay, this answer into this expression here. And I also can then get T1 equals 88 newtons. Again, those are very, very close to my answers here from above. I find this method, okay, a little bit more challenging. There's a lot of physics going on in here, and you guys are welcome to use this method of scalar components. I don't find it as intuitive as the other method, the triangle method, but again, it's really up to you guys to understand these and sort of how these work. Okay, I've got one more example left, and again, another discussion of equilibrium forces. With equilibrium forces, we can look at this particular situation here, and the fact that, if you like, okay, that the resultant vector force is equal to the equilibrium plus the equilibrium force is equal to 0. The two of them are equal to one another, they balance each other out, or the combination of these can be the 0 vector here. So let's find the equilibrium of the following system of forces. We've got three forces again here. Let's find this equilibrium force. So to do that, we're going to find the resultant force and then just take the negative direction of the resultant force to get the equilibrium force. Okay, I'll walk us through this quickly here. All right, let's do it with components. So our Rx vector is going to be the string. I'm going to do start here and do this one first. So it'll be 20 cos of 150 plus 15 cos of 270 plus 20 cos of 0. When I work this out, I get, and similarly, my resultant y component will be 20 sine 150 plus 15 sine, can't borrow all of that, 270 plus 20 sine of 0. And when I work all those ratios out, I get negative 5 newtons. My R combination here is going to be the square root of 2.68 squared plus negative 5 quantity squared. And when I work that out, I get 5.67 newtons here. My orientation, or my direction, is Ry over Rx. That will be negative 5 over 2.68. Gives me, when I take the 10 ratio of that, gives me negative 61.8. So this negative 61.8 is down here. And I should answer my question the way it was given. That'll be all the way around here. That's 60. Let's go 62. Okay, so that orientation, will be, well, that's 20. That leaves me with a 28 degrees. So it can be all the way around as that resultant vector here. So that's 270 plus 28. 270 plus 28 is 298. So my resultant vector is 5.7 newtons, 298 degrees. My equilibrium vector would also be 5.7 newtons, but it will be in the reverse direction here. So that will be kind of like that, where this 28 degrees, I just use so that'll be, that's the 62, and this is the 28. So that would be 90 plus 28, or 90 plus 28 is 118. So that would be 118. Now if you like the bearing orientations, I've got down here in my notes, that would be south 28 degrees east, or north 28 degrees west, if you like. Okay, so that's it for a bit of a long unit here, or section, but that's it for forces, vectors, and there's a couple homework questions that you guys can work your way through. Thanks.